everybody. I'm Miles O'Brien, science correspondent for PBS and a producer of Novas over the years. Welcome to the Nova Nation. We are on the bridge of the Korean research vessel, an icebreaker by the name of Araon, which is a Korean portmanteau for all oceans. And so far on this voyage, which is now, I think, approaching 50 days or thereabouts, it has proven that name to be true. I'm joined with Pete Davis with the British Antarctic Survey, who is fresh from a very exhausting campaign on the Thwaites Glacier to drill a hole in it to reach the ocean beneath. We're on our way back now, all of us. The seas are rolling a little bit, and we're passing an iceberg or two. If I see one, we'll show you a picture. Matter of fact, you can see out the window right now if you want to see what's going on. There's the Southern Ocean today. I think that's probably as calm as it gets in this part of the world. It's 67 degrees of latitude. We still have, what do they call it? The roaring 50s.
The roaring 50s, the furious 40s.
Furious 40s. There's all these
terms to get
through. It would make you scared, of course. We had a very benign crossing coming down right after Christmas, and I feel like we owe something to the karma bank or something, right?
The average has to correct itself. It's going to have to be bad.
Indeed. So we've had, I got to say, Pete, this little background for our viewers before the questions start going in. And we do want you to join this conversation. Obviously, this means nothing as a live stream Q&A if you don't do the Qs. We got A's, you give us Qs. So send your questions whatever platform you're watching on right now. The folks at Nova are going to funnel the questions to us, and we're going to do our level best to answer them. So let's do a little bit of backstory, shall we? We shoved off from New Zealand December 27th. And went on a long voyage to get to Thwaites. That was 11 days of just chugging through the ocean, getting to the Amundsen Sea. And then we get to the Amundsen Sea, and let's walk through this a little bit. We waited no less than, I think it was 10 days for the weather to break.
Yeah.
And so it's very interesting. This time of year, it's summer in Antarctica. It was actually probably a lot colder in Boston for a good chunk of the time. As a matter of fact, I know that to be the case. It was like in the 20s Fahrenheit, but it had a dew point problem. There's a lot of low cloud, and if you're a helicopter pilot on a white ice sheet, that is a real problem. So walk us through those 10 days when you and your team, 10-person team, lots of kit, lots of gear, ready to go, and you're waiting. Tell us, kind of walk us through those 10 days, what that was like.
Well, I think experience it's where your experience of Antarctica really comes to the front, because it's just a waiting game. There's nothing you can do to speed it up. The helicopter pilots, it's their final say. They say if they fly, they say if they don't. So we did everything we did to get ready. All of our kit was ready to go. And as you say, the weather just kept rolling in, that low cloud. And it's kind of hard to picture that low contrast issue. When you talk about low contrast, what the pilots mean is they can't tell the difference between what's snow and what's sky and what's cloud. And they get entirely disorientated when they're flying. That is really not what you want from a helicopter pilot who doesn't know whether they're up or down or left or right. So we have to wait. So during that process, we're keeping an eye on the timeline. How much time do we have left? Do we still have enough time to complete the mission? We went through all of our kit to try and cut stuff out. Can we get less kit onto the ice shelf so that when we eventually do go, we don't have to transfer as many rotations? But ultimately, it was just a waiting game. And there's a saying, hurry up and Thwaites. This is pretty much what happens when you get to Thwaites. Is the weather is bad, you have to wait. Yeah. But then when you get the chance, you jump on it and you hurry up, because you never know when that window's going to shut.
All right. So a lot of people ask me this over the course of my time here. What was the hard deadline which put you under the gun a little bit? This vessel is a busy vessel. Tell us a little bit about that.
So there's a lot of science going on. We're talking about the hot water drilling, but that is only one part of a much wider scientific program that was happening on board the ship. There was a whole bunch of kind of open ocean oceanography. There was a bunch of glaciology, seal tagging, ice thickness surveys. So every single day we were on the ship, stopping the ship from doing other science. There was always that kind of that tension. Yeah. So obviously we wanted to get off the ship as quickly as possible. We needed at least 10 to 14 days on the ice. We really couldn't do the job any quicker than that. So whilst we still had more time than that deadline, we were comfortable, but obviously it was creating tension on the rest of the ship and creating pressure on the rest of the schedule.
Yeah, there was no talk of keel hauling you, but into that.
Yeah.
So we have kind of jumped on a moving ship here a little bit. Let's tell people a little bit about what BASS does. This is a hot water drill,
Yes.
Which is based on the laws of physics, is probably the fastest way to get from the surface of a glacier down to the ocean. And basically, you're an oceanographer who does things the hard way.
Absolutely.
And this is the easiest of the hard way. So explain what you're trying to do.
So fundamentally, what I want to understand is around Antarctica, around 70%, 75% of the continent, there are floating extensions of the ice sheet. So bits of ice that float out over the ocean. And they act like giant dams or giant corks by keeping ice that's on the land. And that matters because if that ice that's on the land gets into the ocean, then sea levels go up. But to get to that ocean, we have to get underneath the ice. And we have lots of modern technology with robots and stuff, but there's a limit to where they can go. They can't go right to where that ice first starts floating, that grounding line, as we call it. So this is where hot water drilling comes in. It's the only way that we can get an access hole through, in this instance, 1,000 meters of ice to that critical ocean underneath to really understand how the ice and the ocean's interacting.
So it's hot water down a hole. It's a very straightforward in that respect, but it's all in the execution.
Yeah.
Getting the kit out there, setting it up in difficult conditions, making sure you got everything kind of working scientifically. I remember I went out there, you had just begun drilling, or you're in the process of drilling, and you were kind of way off on the edge of the safe zone because it has to be staked out for potential crevasses, for underground cracks, which could be fatal. And you were right on the edge, and you were like banging away on your tough book, trying to figure out something. And there was quite a bit of stress in it. Walk me through that little moment.
Yeah, so when we get out onto the ice, so when we arrive, one of the first things we do as the scientists is get all the science kit out and test everything that's working, because it's gone from the UK, it's been shipped off across the world, it's then taken across the Southern Ocean into a helicopter. These things, they're sensitive equipment. They always have little things that need fixing. So I'd had everything out. Everything was working. Everything had been fixed. And then on the morning of the beginning of the process of deploying, I was like, right, let me double check it again. Nothing was working. And at that point, your heart is in your mouth. Like, oh, geez, I'm gonna have to slow the drillers down, tell them that we're not ready again. But fortunately, I've had this issue before, and usually it's because of the drill. It's creating a lot of electrical noise. There's a lot of volts running around the shop. So I basically took everything, put it in a sledge, dragged it as far away as I could from the drill, which isn't that far in this instance because we had a small safe area, and tested everything again. Unfortunately, it worked perfectly. So I was able to convince myself that it will work. When the drill gets switched off, we'll be good to go.
So you breathe a sigh of relief. But wait, there's more to this story. In the meantime, let's get Mary BBH3Z's question is, what is the most surprising fact you learned on your adventure? Do you have one?
So I think we learned a lot. We've learned a lot about the ocean underneath. It's very warm. I think that's what we were expecting.
Yeah.
But what we did learn is how quickly it's changing. We did a bunch of profiles where we measured the temperature and the salinity over the whole depth of the ocean under the ice. And usually most ice shelves, they're quite sluggish. They don't change very rapidly between each individual cast. And these are only maybe 20 minutes apart. Whereas under Thwaites, they were changing big time. And those big changes are indications of how quickly it's melting, how much energy there is in that system. I think that's really surprising.
Yeah, and what you're interested in, what scientists really want to know, that we know there's warm water under there, but what are the processes that is making it melt so quickly?
Exactly.
And one of the things I would say, my surprising fact, one of the details I learned was this role of subglacial discharge, which is to say, there's fresh water, there's a cushion, if you will, of fresh water between the glacier and the land beneath, many thousands feet below. And the water is, there's friction and geothermal, and which keeps the water liquid. And of course, this allows the glacier to slide a little bit. But what's interesting about it is the idea that this subglacial melt, which is a little bit warm and fresh, squirts into this same spot where you're drilling.
Exactly.
And that creates like a turbulent churn. And that might be one of the processes which causes it to melt more, because warm water that is just sort of stagnant is one thing. Warm water that's turning around is different, right? Walk us through that.
Exactly. Yeah. So the fundamental process is there's a lot of heat in the ocean. There's a huge amount of heat in this ocean. How does it get up to the ice and then into the ice? And that's all through turbulence. Now, turbulence is the kind of the real small scale motions that you see when you add milk to a cup of coffee and you stir it, or in a river that's going over rocks. We want to measure that. And this subglacial discharge, when it comes out, it's coming out like a fountain, and it spurts out and it mixes everything up, and it can grab heat from below and drag it up to the ice base, and it all kind of acts together to get the heat from the ocean into the ice and to drive melting.
All right. Keith Kahn wants to know if I've been on any EVAs, extravehicular activities. He's a space guy. On this mission, I did get on the helicopter and go to the glacier, so I would count that as an EVA. I got off the boat. So, all right. So let's go back. So understanding the processes, and which is what, the main goal of what you were doing. You got some instantaneous readings, which actually are unprecedented. No one's ever got numbers in us. I'm converting to Fahrenheit, but basically 5.5 degrees warmer than the freezing point of glacier ice in seawater. So a 5.5 degree Fahrenheit spread. So that should get your attention right then and there. And then when you start factoring all these other processes that may be at work, causing churn and other things that might be eating away at that glacier, it is of great concern. But what you really wanted to do, of course, was to leave devices there on a permanent basis, or semi-permanent, a year maybe,
a year or two.
So, all right. So tell us, first of all, what were the instruments you wanted to leave, and then we can talk about what happened.
Yeah, so we wanted to leave a bunch of instruments in order to monitor these conditions, the ocean conditions, for 1 or 2 years, because these profiles are great and they tell us a huge amount, but they are a snapshot. And what we want to know is how do things change in time. So we had a lot of the similar instruments to record temperature, to record salinity, to record current speed, basically to tell us all the physics of the ocean. And the idea that they would be left behind and they'd send their data back in real time to kind of allow us to answer these questions going forwards, as well as just as a snapshot.
It's kind of hard to overstate how important that would be for scientists to have that kind of continuous stream of data. Anytime you can get, a weather station, for lack of a better term, you're I mean, all of a sudden your data is going up by orders of magnitude.
100%. 100%.
So what happened on the way down?
So it's a sad story. They got frozen. They got stuck. Ultimately, when we're hot water drilling, our biggest enemy is refreezing. We melt the hole with hot water, and as soon as the heat is dissipated from that hole, it's refreezing. It's closing in, and the closes in.
This is really, really cold down there. We're talking 2,000 feet below.
This
is cold as you can imagine, right?
Exactly.
Many, many degrees below. So it's not just 32 degrees kind of thing.
No, it's the refreezing rate is about 0.5 centimeter in diameter per hour.
Okay.
So we drill a 30-centimeter hole. So it gives 30 centimeters, gives us a window to get everything in the hole before it gets too narrow. The reality is because of issues with the drilling, because of the challenges of working where we were, the hole had narrowed more than we expected it to. It had narrowed to a point that we were unable to get the instruments through, and they got stuck. It's a risk. We are very much pushing at the forefront of science here. Pushing at the forefront of hot water drilling in these difficult regions, and sometimes you don't succeed. It's a real shame.
Yeah, I want to talk about that a little bit. Let's get at 60s born 26's question. After the equipment got frozen in the hole, what happened the next few days? I watched a lot of your info on this with a few different YouTube channels, but I haven't seen anything past that. And forgive me, at 60s born 26. We were all exhausted. If I was exhausted, I know they were. I've got a piece coming out for the NewsHour in a couple of days, and I did take a little bit of a break after it all happened. But basically, what happened was you guys didn't waste any time packing up camp. I mean, essentially, right?
No, absolutely. So part of the reason we were so pushed for time was because the weather was closing in. We talked about this at the beginning. The helicopter pilots can't fly if there's not great weather, and the weather window for taking us out appeared to be narrowing. So we knew we were up against a time limit. So as soon as we finished, and as soon as we hadn't succeeded in deploying the mooring, that was maybe 3 or 4 o'clock in the afternoon. We pretty much went to bed. We woke up the next morning and we started stripping the camp out. And by the end of that day, we were all back on the ship. All the kit was off the ice except the tents, and that was the end of the season. And this is the fastest I've ever gone from finishing a drill hole to being back. Okay, we rarely work off shift, but at least being back on a ship. Usually that second day would be a complete rest day. Nobody would be moving. We are exhausted. We've been up for 30 hours, 40 hours. with very little sleep in between. But that's the nature of working in Antarctica. You can't second guess the weather, and we had to move.
Wow. Wow. So really no time for sentimentality. You got to move.
Yeah,
Yeah.
the ship had sent the forecast. The helicopter pilots were waiting, and it was up to us to get up in the morning, get the kit done, or get the kit down, and get it shipped out ASAP.
All right. So a couple debrief items I'd like to get from you. First of all, I'm no expert, but I do know that this particular site was as challenging as you have ever encountered, and that's by design. This glacier, because it's not just melting, it's breaking apart like crazy. It's traveling every 30 feet a day, and it's accelerating as it reaches the Amazon Sea. And it's just a chaotic mess as it breaks up. And the idea was to get as close to that chaotic mess right at the grounding line before it really gets ugly, and figure out what's going on there. But that's still a very complicated place with a lot of underground surprises.
Yeah.
As you drill down, what did you run into?
So as we drilled down, so we knew around the outside of our safe area there was a lot of surface crevassing. But what we weren't able to see is what was happening underneath us. We didn't have the radar that could penetrate that far. But what we found is that 20 meters beneath us, between 20 and 30 meters, there was a gaping open crevasse. And it's okay. We can drill through air, but it creates a lot of complexity. And I think at this time it caused the holes to deviate. We have two holes together. They widened during that air-filled section, maybe because we know blocks were falling off the roof of the cavern, possibly pushed the drill hose out. It stopped us getting the drill hose down and back up at certain times. So it really slowed down the whole process. So you're right. This is very much the hardest place we've ever had to hot water drill. The terrain was challenging, the weather was challenging, the drilling process itself was challenging. So unfortunately, this whole combination of circumstances probably is what resulted in us not succeeding.
Yeah, I mean, I'm imagining that, this high pressure hot water fire hose, almost at the boiling point, 90 degrees Celsius, 192 degrees Fahrenheit, going into an open cavern. That's not going to go well. No matter what, I mean, that's a problem, right?
So we have an exceptionally heavy drill nozzle for exactly this reason. Right? Yeah. So we have a very heavy brass nozzle that's about 1.5 meters tall to keep the drill vertical. Because if the drill is moving around like this, then game over. But what we can't account for, or what we don't account for, is things falling on the drill hose when it's underneath the ice.
Right.
The ice should be solid, So I think, we've learned a lot about this process. We've learned a lot about how now to drill through these air-filled caverns, how to perhaps try and mitigate this next time. Probably drilling an awful lot slower through that air bit. Usually the initial 30 meters, you drill quite quickly. It's not really solid ice yet. It's still more kind of snowy. You can melt through it pretty rapidly. But probably that speed is what counts against you if it does get knocked off. You want to be probably a little bit slower. But this is a lot to learn,
So that's one, maybe a little slower at the outset in case you run into a cabin like that. The other thing that occurs to me too is because you're going to want to be in another complex place. That's by definition, that's what you're after, right?
Absolutely.
So you guys, once you start drilling, I don't think people appreciate this. It's pretty much 36 plus hours nonstop, right? You don't stop, because if you stop, it freezes.
Exactly. Yeah.
You have to keep going.
Keep going.
And this puts a tremendous, I mean, you're already exhausted getting to the point of drilling, getting everything set up. They have to shovel 20 tons of snow to melt in order to create the hot water to go down the hole. So you're already, you've done Olympic level shoveling, then you got to set this thing up, and then you got to stay up for, 3 days essentially. Maybe, almost 3 days.
3 days, basically.
So what can you do to because fatigue has got to come into this, right?
Yes.
I mean, do you think that did you guys, because you were tired, if you were a little fresher, would it have been different?
It's a really good question, and it's a really difficult balance, because ultimately the answer is probably more people or more time, but both of those things are not easy to source in Antarctica. We could bring a team twice the size, but then it may have taken us twice as long to get the kit onto the ice, and we wouldn't have succeeded because we wouldn't have enough time. Or we have twice the length of time, but then the cruise itself is limited in the length of time it can be away. So there's a sweet spot, and I think our experience at Bass, I think we have some very, very experienced drillers, so they know what they're doing. Even when they're operating right at the limit of their capability, they still have a fantastic capacity to know how to drill and the behavior of the drill. There are things that we do in terms of we have lots of checklists, lots of tick lists, things that we can just go through to make sure that everything's operating correctly, to try and take away some of that mental challenge. But ultimately, this is what we prepare for all year, for coming down for those 3 or 4 days of that pressure where we have to get the job done. We've thought through all the different situations already. We've kind of gamed them out in our heads. So hopefully when it happens, we make the right choices despite the fatigue and despite the challenge that that's presenting.
It's tough. It's superhuman. So you wouldn't necessarily put on your list of things to do differently, bring more people. That's it. There's like trade-offs within trade-offs in your business, right?
Exactly. Yeah, if we double the size of the team, then the weight of equipment, food, tent, safety gear has to go up, and then that's more helicopter rotations to get everybody into the field. So it's not a zero-sum game. We can't just throw 50 people onto the ice and not be impacted by it.
It's like the difference between the Scott and Amundsen expeditions, right? Scott went big and didn't go well, right?
Exactly.
Amundsen, couple of dog sleds, and he made it, right? Question from Jovan 9768. Will you attempt the same project again next year or figure out a different way to get this data? And I should tell you, there's an important meeting, which we are not invited to today, with the team to discuss this very issue. Next year, not for sure. It's too soon, but it would be 2 years. So go ahead and talk about the possibilities.
I think the South Koreans, so the leaders of the expedition, they have a program to come back here every other year. So I think to answer the question, is there any other way? I would say no. We can't use satellites to see beneath the ice. We can't use autonomous technology to get that far beneath the ice. It has too many technological limitations currently. So yes, I think we will be back. We will be using the same methods, but we informed by what we learned this time, and hopefully second time around we'll have more success.
So there isn't a better mousetrap than a hot water hose going through.
Ultimately not. You know, fundamentally, to melt a volume of ice, you need an amount of energy. We can't break that. We can't break the laws of physics. We can't use half the amount of energy. So it just comes down to efficiency. How efficiently can you deliver that energy to get through the ice? Now, our hot water drill is about 80 to 88% efficient. We could make it more efficient, but that would require more equipment, heavier.
Again, same story.
You might have to burn more fuel to get onto the ice, and may take you longer to get onto the ice to maybe drill the hole quicker. So there's those trade-offs there. It's not it's not a simple win just to say, oh, we'll double the amount of weight so we can drill at 90% efficiency.
It seems very similar to the kinds of problems that engineers face when they're building a rocket, for example. You know, the amount of fuel, you want to go a certain distance, but as you add fuel, you have to, everything becomes, you start chasing these tail a little bit.
You can't break energy, basically.
No. So, all right, if money's, this is Dayton Cherry Chicken. If money, scheduling, personnel, and equipment were no object, unlimited, be available, what would you like to invest in?
Oh, what a wonderful question. I wish this was the world. So my answer would be many more drill holes.
So just come same place though. I mean, this place in particular is of great interest.
Yes,
right?
but West Antarctica in general. Thwaites is this keystone glacier. It's probably the most critical, but surrounding it are fundamentally important ice shelves and glaciers as well. And I think it sounds bad. We are drilling one hole in the size of a piece of ice the size of the state of Florida, and we're learning a huge amount, but fundamentally it's one hole in a state the size of Florida. If money was no object, I would like to pepper the place with holes to really fundamentally understand how the processes change with space. How do they change with time? How do they change under all of these different glaciers, all of these different ice shelves? We know more about the moon, I suspect, than we do about the underside of these critical systems. So I'd really like to throw in an ideal world everything we have at it to really understand it, because what happens down here doesn't stay down here. What happens to these glaciers is going to affect sea level rise in the US and the UK, wherever people live close to the coastline. What's happening here really matters.
It's very important. And people ask me this all the time. Well, why would you drill a hole in something as unstable? If you dig a hole in Orlando, you wouldn't expect the Florida Peninsula to come off.
Exactly. These are tiny holes.
Frick, it's actually a stretch, I would think. Okay, Keith Cowing, my space friend and good friend in general, is wondering if you have thought about how Antarctica science informs us on how to conduct astrobiology missions to Europa and Enceladus and beyond. So icy moons.
Yeah.
I've thought about this a lot. Particularly, there's a project on here, Keith, involving an ice penetrating radar using long wavelength radar to peer through the ice to see the terrain beneath, which is a big part of the story as well, because how rough it is, how it slopes toward the pole, where it gets smooth, how much water there is, all that affects the speed at which Thwaites might collapse. And that very radar is going to be on the Europa mission, which is doing the same mission. So there is a direct application there.
Yeah,
But I
yeah,
keep thinking about space missions and the
yeah.
way you guys do business.
No, 100%. And I think there are lots of crossovers. I think in hot water drilling, we have clean drilling, we have dirty drilling. Now, that dirty drilling is not dirty. It just means that the water we're using is not biologically clean. But we do have projects that drill into or want to drill into subglacial lakes. So these are lakes beneath thousands of meters of ice to understand if there is life living down there, what sort of kind of bacterial communities. And there we have to drill cleanly. We have to ensure that the act of opening up an access hole to that lake does not introduce bacteria and viruses into that lake. So there, I think there's a lot of crossover. Similarly, to do something to Europa, whatever we do, we need to make sure it's clean. We need to make sure that we didn't take something from Earth out to those planets, and when we're drilling through. So there's a nice crossover there. And also some of the technologies we use. So we've recently worked with kind of remotely operated vehicles that we can deploy through the borehole. So these are tethered to the surface. So they're kind of different to the sort of things you deploy at the ice front, but they're tethered to the surface, and you kind of send them down and they can go out exploring. And they're fantastic because you can get this amazing view of what's happening around a single borehole. And I suspect the technology that goes into developing that sort of through borehole instrumentation is probably very similar to the sort of technologies that we would eventually want to send to a planet like Europa. Obviously scaled down because these are 2 or 3 meters in length. You want to bring them down to something space satellite size, but that's beyond my my field.
But NASA, if you're listening, this is a good place to come. I know, of course, as Keith well knows, and I've been up there with him, that NASA does go to the Arctic quite a bit, to places like Devon Island to learn a little something about operating in extreme environments. But if you're really thinking about icy moons and getting through thick sheets of ice, it would seem to me a mission here to sort of sort out the problem of figuring out how to drill through I think the Europa ice sheet is many, many miles thick.
Yeah.
And obviously you're not going to bring hot water there. You got to figure out another way.
Got to figure out another way. Yep.
Some sort of, heated, what would you call it?
Some sort of heated probe, some sort of probe that slowly, very, very slowly melts its way through the ice. It's probably refreezing behind it. You're not going to hold the whole.
You have to bring your data with you.
And then you're going to be uncoiling a wire as you go. Probably some sort of nuclear power, which obviously we can't use in Antarctica because of the treaty. So yeah, there's definitely technological crossovers. But I suspect what we're doing here and what eventually will go to space, they won't ever look the same. But you can probably trace the lineage back to the original.
Well, this is my favorite planet. We might as well learn about it, and if that helps learning about other planets, I think that's all for the better.
There's a huge amount to learn here still.
Yeah. So you and your team, no rest for the weary. You're thinking about your next efforts and campaigns.
Exactly. Yeah.
You're going to do a little planning here today. What lies in store for you? You got a 5-year-old at home?
Yeah, I got a 5-year-old kid at home. Yes.
Be able to spend some time there.
Absolutely.
This is a lot of time away, and quite frankly, a big sacrifice. Obviously, it's worth it to you, but just tell us what your life is like here on out.
Yeah, so we, as the team at Bass, we pretty much have a whole drilling season from now until the beginning of 2030, pretty much every season. So coming up at the end of this year, next season for us would be on the Ronnie ice shelf. So it's a very different ice shelf. It's more in East Antarctica. It's much thicker. It's much quieter. It's not evolving anywhere near as quickly as Thwaites. But we have a long-term monitoring time series there. And although Thwaites is all about understanding processes, what we also need to understand is kind of long-term variability. How is the Antarctic system changing in time? So we drilled a hole at this exact location we're going back to 10 years ago. We've had data for 10 years. We're now going to go back, drill a new hole, deploy new instruments, and they'll give us another 10 years of data. So we're building up these really long time series of kind of environmental change that we can use to baseline changes that we see in the future. And then after that, every single season we're busy. We have a season in the Arctic and Northwest Greenland, followed by possibly another season down here in 2 years' time. Then we're going to be working in Riser Larsen, a smaller ice shelf in East Antarctica. And then after that, we're maybe back on the Filchner ice shelf. We're kind of getting out to the point where we're still winning money for this work. So it's a fully committed team to keep exploring Antarctica.
Well, I know BASS, the British Antarctic Survey, has faced some budgetary challenges. At the very best, flatline. And of course, in the U.S., it's a much more drastic picture as budgets have been cut. Make the case for this. This is, first of all, in the grand scheme, certainly relative to the problem and its impacts, This is a tiny pittance of money that's been spent on just on this mission to try to understand something that could potentially raise sea level all over the world by 10 feet if you count the glaciers it holds back. That's a stunning thought right there.
Yeah.
Make the case for, the investment in all of this. Why is it worth it for taxpayers to fund this?
Well, I think, as you just said, fundamentally what happens in Antarctica isn't going to stay in Antarctica. If the planet continues to warm, if we continue to emit carbon at an unabated rate, we will see a collapse of West Antarctica in 200-300 years' time. And that is 2 to 3 meters, 10 feet of sea level rise. And that's 10 feet everywhere, the entire globe, on average, up by 10 feet. It's an average, it'll be higher in some places, lower in others, but that is catastrophic impact on coastal communities, on massive cities, New York City, London, right by the coastlines. These cities are not going to be able to survive that level of sea level change. So we need to invest now to mitigate that change, and to be effective at mitigating that change, we need to know how much sea level rise should we expect. And that's where we fundamentally come in. We want to tell governments and society how much and how fast, how much sea level rise are we going to get, and how quickly is it going to happen, so that we can mitigate it and plan for it back in the UK and in the US. So the money spent down here is tiny compared to the cost of mitigating and the cost of protecting these societies. So I think it's money well worth spent, or well worth being spent.
Do you is it worth it, the sacrifices you made? Do you love what you do?
Yes, I absolutely love what I do. I keep telling my wife and my son, I wouldn't be here if I didn't love being here. The sacrifices that everyone has to make to be here are enormous. You miss Christmases, you miss birthdays, you miss New Year parties, you miss seeing your friends over the festive period. Everyone here is here because they fundamentally believe in what we're doing. And if people didn't have that conviction, or they didn't enjoy it, then really they should just spend time with their family instead. That's probably the most important thing in life. But I believe what we do. I really enjoy coming down here. I love working in these remote places, and I will continue to do so.
There are people out there that actually believe climate scientists are in it for the money, and I would challenge them to come with us on this voyage to be dispelled of that notion.
Yes.
Jovan 9768 says, "Thank you for bringing us all along on this incredible adventure. I was pretty depressed when the instruments were frozen, but I am inspired by your persistence. So take it with you."
Thanks for your lovely message.
Yeah,
that's very nice.
Stay with it, Pete, and maybe we'll be back with you here in another couple of years. Who knows? Yeah. Congratulations on successes and moving on from and the lessons learned here.
Thanks very much. And thanks very much for having me along.
Okay, we're going to bring in now David Holland. If you'll take that microphone off, and David's over in our green room. In the meantime, I'm going to give you a shot out the window just so you can see what's going on here. We are pretty much in the soup here at 67 degrees of latitude. We are steaming along at ripping 12 knots. And which means we have about 8 days of travel to get to Littleton, New Zealand. Then we have to spend one more night on the ship because of customs requirements. And then on the 19th, we'll start making our way to the airplanes back to terra firma. And for us, our journey began on December 15th, going to Auckland and doing a story on fabulous, interesting company called Rocket Lab. Allison Hashimoto, 5765, a dear friend of mine. It's been so exciting to travel along with you on this adventure. Where to next? What's the next scientific mystery you are going to cover? Allison, I got to say, I am increasingly focused. As you know, we've talked about this a lot. I am focused as much as I can now in my reporting and filmmaking on solutions, driving toward solutions to big problems, and meeting people like this character, David Holland, who we will get to know here in a moment. I've got to switch out the camera here. You're seeing, sorry, this character. I am interested in solutions, and I am really interested. As you know, Allison, and a lot of people know out there, I live on Cape Cod. I live short steps from Buzzards Bay. I live a few miles from the Woods Hole Oceanographic Institution. I've always been interested in the ocean and its health and the science associated with it. And I'd really, this, of course, even though it's about ice, it really is about oceanography as well, and has just redoubled my interest in trying to tell the story of what's happening with the oceans, their importance, their value to all of us, and quite frankly, how we mistreat them. David Holland is now with me.
Hey, Miles.
It's good to see you. The Nova audience is happy to see you. And a familiar person to the Nova audience, particularly if you're interested in understanding the Coriolis effect, which is one of his specialties, right?
True that.
Yeah. Anyway, so David is with New York University. He's a mathematician and a glaciologist. And a couple things. First of all, let's talk a little bit about your direct role in, since we were just talking to Pete, you had an instrument which you ended up deploying, but it won't do exactly what you had hoped. Tell us a little bit about, because he actually enlisted me in the process of deploying it, which was actually quite comical, having his one-armed buddy helping him pull batteries across the glacier. But tell us about that instrument. And first of all, was it, to the extent it couldn't get down to the ocean, so it's a limited success, but is it working at least?
Yeah, but I wouldn't call it a limited success.
What would you call it?
I'd call it a failure.
Well, you did your job, right?
No, we have to call a spade a spade. We fail, and we go back at it. But this is a failure.
Yeah. All right. Well, let's put this in perspective then. You've been to Antarctica how many times?
A dozen.
Okay. And the last time, 4 years ago, this very ship, that helicopters, pretty much the same configuration. Sea ice didn't even allow you to get two thwaites, right?
Yeah, I was looking at the sea ice today. This year was kind of normal, and 4 years ago it was a little bit excessive.
Okay. And previously you had, there was a hot water drill hole drilled, like, I guess the year or so before, but not in 2 years before, but not in the critical place.
It was the other side of thwaites, less interesting.
Right.
But
so the fact is that this is 0 for 2 now, I guess, for the grounding line itself at thwaites, right?
Right.
So put that in perspective. Is this there's going to be some debriefs today with the hot water drill team and the Koreans, who have now taken a strong leadership in polar research all over the world, which is really exciting to see as the U.S. retreats. Exciting to see them step in. They're going to be thinking about what's next. What would you recommend to them?
A complete change of perspective into we're looking at a problem that we're trying to solve, and we're running up against two things. One is we're fascinated with melt, and melt is 50% of the problem. The other 50% is braking, which you alluded to earlier. And as we were flying through those canyons and screaming as the pilot, we were going through
a little bit like Star Wars.
There's one part with the canyon, we're going through the helicopter, very safe, but it pinched. And then the pilot pulled up and said, let's make sure we get
I would say the better part of valor on Dominic's part, that case, right? Anyway.
So that really brings out that when glaciers move fast, they break and they fracture. And a lot of the processes to do with ultimately Thwaites' demise or not will have to do with fracture and cliffs failing and that. So that's half of the problem on which we have no perspective, no math, and no progress. So our goal to provide society a forecast, same as on your iPhone, right? The weather forecast, which have been pretty good, wouldn't you say?
Yeah, actually it has.
Yeah, remarkable.
We're right in the middle of what I saw earlier today, that's for sure.
Yeah,
right
so it's nothing but a glorified form of Newton's second law with a bit of other stuff thrown in. But we're not there. And kind of like with earthquakes, if you live in San Francisco, you're thinking, well, when's the next fracture? We don't have that skill set. We don't have that nailed. And so we're kind of stuck in the bigger picture in we can do what we can do. We're comfortable understanding melt and thermodynamics. We're not comfortable with fracture. And we don't have that impetus to go after that part of the problem. So that's that part. But there's another layer outside the onion, which is that really, if what people are talking about as we move to solutions, which we'll jump to in a moment, and maybe we can get some questions too instead of less talking.
Yeah, no, you keep going for a bit.
Okay.
People are thinking.
Oh, they're thinking.
You're throwing a lot at them right now. They're processing. Keep going. Keep going, Professor. There will be a quiz, people. So make sure you get on the Coriolis effect. As a matter of fact.
Yeah, you're giving away the exam.
Yeah,
so yeah.
Go ahead. Was this be on the exam? Anyway, go ahead.
Penguins will be on the exam.
Yeah, absolutely.
So if you peel back another layer and you ask the question, I don't know, someone's typing, okay.
Yeah.
If you peel back and you ask about what is it you can do about some of the problems, and there's a handful associated with changing greenhouse emissions, right? There's from Has anyone noticed the amount of smoke in Canada and the United States this year? I have to say, I was never so terrified in a long while. On my phone in Canada, every 2 weeks, it said, 10 minutes, prepare, take your pets and children, both, evacuate.
Right.
And there was 10 kilometers away on fire. It's never happened. The whole peninsula was on fire. So there are a whole bunch of perspective problems. This is one of them, called sea level. But there is the fact that the oceans are becoming acidic. This is really simple chemistry. So there's that part, and then there's a part that you want to turn to, which is solutions. I find the part that I focus on not depressing, but I think it's not uplifting.
Yeah. So that pessimism, that depression, whatever you want to call it,
Yeah,
has led you to kind of step outside the scientific mainstream a little bit. We're talking about a geoengineering idea that's out there.
yeah.
That would mean there'd be a sea curtain built sort of at the gateway to Thwaites. There's actually an undersea valley there.
Like the Grand Canyon.
The Grand Canyon, which would hold back some of the warm water potentially. First of all, how did you get into that idea, and what has the scientific community told you about what they think about it?
Oh, what the scientific community thinks about it is kind of doesn't really matter. What it is a question that has to be investigated. So we are faced with this thing again. The elephant in the room is the carbon, and the carbon works in very complicated but clear ways that we understand. I'll just diverge for a second. How does carbon affect the grounding line meltwater at Thwaites? You would say, well, the temperature is getting warmer and it's warming the ocean and the warm waters. No. What's happening is because of our Earth, the way it works, in terms of physics, if you really get your head around it, there are planetary waves that you call high and low pressure. You look at them on the map every day, right? Weather forecast. These waves are guided by the temperature gradient on the planet that's changing. And lo and behold, emphasis on low, Amundsen sea low, has changed in a way that brings warm water to this part of the Earth. Totally complicated, not obvious, just like if someone was like a neurosurgeon, they would explain what's going on with your brain. You just say, I got it, you studied it, this is how it works. That's how this thing works. And so that whole carbon thing is transforming the planet. And so one group of people say, let's stop the carbon. That's called mitigation. The other people say adaptation. That's called suck it up and live with the carbon. So that's a bigger picture question, but that's forefront. And within that context, if you're going to adapt, what are you going to do? And the curtain is one of dozens of ideas.
So that idea is in the mix. How does that factor into the work you did here? You deployed, in addition to the temperature sensor that went down the hole, which would have provided continuous temperatures from the surface to the seafloor. Unfortunate that that's not going to happen. But you also deployed a couple of robotic buoys, sort of in that canyon area, which will help scientists understand the currents, the salinity, the temperature. Just kind of characterize the undersea world there. Tell us about that.
Yeah, so that's over studying this over many years, one becomes familiar with the environment and the fact that from the Pacific Ocean, where there is warm water, to Antarctica, between the two is a canyon, and the canyon has sills or hills running across it. The warm water is really salty because it comes from the tropics. And so that water is pouring downhill from the Southern Ocean towards Antarctica in this canyon, principally. So one could conceive to block it, kind of like a dam idea, holding back water. Does that have an adverse impact on the local environment? Hell yes. Why wouldn't it? Then the world has to figure out, well, what about if the other parts of the coastline of the world flood and ecosystems are destroyed by Thwaites because of carbon? So that's not for me, that's for the world. I'm just interested scientifically that I see this as a plausible solution. And I think it's one we need to investigate over the next decade. Would this work? And then if it works, at least it might buy some time. Ultimately, the problem is still out there. The elephant is still in the room, but you could put it at bay with such solutions. Now, some people think that's wrong. I could care less. The point is we need to do science, do research, and provide blueprint of solutions. This is just one, but again, you have to think about ocean acidification, forest fires, other problems. The Arctic sea ice is vastly disappearing, and people are trying to figure out ways to cling on to that. These are major engineering problems. The world has to face it. It's not going to go away.
If the world, you know, if you could wave a magic wand and the world would stop burning fossil fuels tomorrow,
not going to happen.
what would happen? Okay, I realize it's not going to happen. But as a thought problem here, would that be enough to stop the melt and the advance of the collapse of Thwaites?
It may not. There's a word called inertia.
Yeah.
The ocean is a flywheel. It has a 1,000-year memory. The atmosphere has a 2-week memory. So the ocean, once you set it in motion, is a flywheel. And it's been in motion for 100 years now of change.
All right, Dayton Charity Chicken, back with another question. Are you concerned about, I love it. It makes me hungry. Are you concerned about potential changes to the jet stream's currents?
Yes, and they've already changed. Again, I was going back to our planet at one level is simple. It's a sphere, and it's cold on the top, warm in the middle, right? Mm-hmm. Right now, we're warming the top, not the middle. What I'm trying to say is the only reason we have wind on in this planet, the only reason is because it's cold at the poles and it makes air move. So what's happening is the temperature is warming at the poles. The Arctic is on fire. It's 4 to 7 times warmer than the rest of the planet. And so what's happening is that temperature gradient is breaking down. And the thing called the jet stream, which you've been in, right? You're going USA to Europe. Yay, faster airplane, go pilot, go. Jet stream, that thing is beginning to become unstable and it's breaking out. And in the US today, what do you have? Polar vortex. It's that jet stream becoming weaker and breaking out. So these are the transformations you see happen as you meddle with your atmospheric composition. It's fascinating to watch it play out in real time. And that's it.
All right, this one, catastrophic Canon 3-4. This is more like a treatment for Jurassic Park Antarctic edition, but are there any ancient frozen penguin
eggs? I knew there'd be a penguin question.
We did a thing for some first graders the other day.
They were great.
And every question, did you see a penguin? Did you see a penguin? Did you see a big penguin? What kind of penguins did you see?
It was beautiful.
They're adorable. That's all they wanted to know was about penguins. They couldn't have cared less about ice or anything. But no, there are no ancient penguin eggs that can be hatched that we are aware of. But I think you should start working on that movie treatment. I think there's great potential for that. David, you are fully bipolar. You're going to spend a good chunk of the first part of the summer in Greenland. The mask you
discussed. Greenland is much more accessible. It's the same processes, so why not go to Greenland? Much easier.
All right. So what are you going to be doing there this going into May of this
Really
year?
Focusing on fracturing of ice. We're using radars and other instruments. We're going to set up, and now with Starlink and whatnot, satellite communications, we can pour out seismic data real time that we've never been able to do before.
All right. So Marianne Hagen, your friend.
There you go. Hello, Marianne.
Is wondering, she wants a few more details about the robot moorings and how things went with that.
You would.
We had a slight injury on one of them, which means it will not be able to detect current. But interestingly, it is on the less important side, and that has something to do with the Coriolis.
Yeah, so the water pouring in, of course, in the southern hemisphere flows to the left. So in the canyon, the water going into Antarctica is on the left. And that's where we have a key robot, not exactly where we wanted on the main sill in this canyon, We have it on the second best spot. There was just too much sea ice on the main spot. So the robots are in, they're going to go up and down. Right now they're doing daily runs, in fact, hourly at the moment.
You hope.
Oh, I think they are.
Yeah, you're feeling strong about it.
Yeah, that's a very clean, simple technology. An iceberg may decide to do otherwise within a year, but we put them fairly deep into the water, and we just want to see that warm, salty water coming to Antarctica, how much of it, how high, and how fast. That's the kind of information over years can lead to, and again, we are doing zero wall building. We're not dropping a rock in the wall in the ocean. This is all virtual. This is all pure science, pure engineering in the virtual sense. So we want to build these things conceptually. Other people and the world have to decide whether or not this is ever implemented. So I want to make that line super sharp. I think people get confused. So again, no wall.
Well, I do have to confess, we dropped 2 drones in the ocean. So we might have.
You just
I have this phrase. The idea of using Greenland, say, as a laboratory for an idea for a sea curtain.
That's a really bad idea.
It's complicated there because people live there,
yes.
and there are jurisdictional issues which you don't deal with here in Antarctica. Why don't you walk us through that?
Right. So Greenland belongs to Greenlanders, and they will decide what they're doing with their land. We work a lot with Greenlandic researchers, and we collaborate on projects. And so in this case of geoengineering, we're not going anywhere near that. That's their call on how they want to deal with their land.
Okay. So you're going to have to learn other ways. You'll figure it out. But I assume once you have the data that you're hoping to get with these robot moorings, a fair amount of the work can be done with computer simulations.
Unbelievable. Do you realize that now with car crashes, when you build new car models and you build safety systems, it used to be you would drive a car with a dummy into a wall?
Well, I think they still do that, Dave.
Less so. Yeah. And that, first of all, is just a lot of fun.
Yeah,
right.
I think that's part of why they do that. Yeah.
But now that can be done on computers. That can be done with yes, absolutely.
Yeah.
Just like AI is taking over medicine. If you want now a diagnosis of your cancer, do you go to a bunch of doctors and get opinions? That day has passed. That day has completely passed. And so it is with many things. Digital twins, virtual modeling is it. And people haven't caught up to that yet. But a lot of that's changing. And so therefore, you can do virtual modeling of our environment. And some people can naysay and say, we don't know this and this. No, check out your weather forecast. It's amazing.
All right. This, you've had a long career going to Antarctica, and you told me this is your last voyage. Why is that? And do you feel like you've accomplished all you set out to?
Yes, absolutely. It's been a really fun ride. In a way, it's a shame that more people don't get to experience Antarctica, particularly when you're with yourself and another person out on a glacier for a month. That's a very special experience, just to really get that this is the entire planet. You're at the end of it, and one end of it, and that's all there is. It's really a kind of a religious, transformational experience about the planet. I'm sure a much deeper one is to go out in space and look back at the Earth.
So why are you quitting?
Not quitting.
Well, why are you not coming back to Antarctica?
Oh, because lots of other people can do this. And also, I think, so first of all, I train lots of people. I have students trained, professors around the world. They're actually coming on the next leg here. So pass the torch. You don't want to be doing this all the time. There's lots of people can do this and be trained. And the other thing really is that ultimately, more and more people here in ships is not a good idea. What you want is preparing, thinking again, spreading out across the solar system and beyond. It's going to be automation. It's going to be robots. It's going to be artificial intelligence. It's going to be lots of things. We need to get moving, and Antarctica is a great place to start that. So I would say, first of all, I've known a handful of people, my friends actually, who've not been successful in coming back from Antarctica. It's a dangerous place. We don't need humans here, really. We need automation and exploration.
Can it be done? I mean, things like that hot water drill, could you come up with a way to do it robotically? And again, this brings me back to the space analogies. It seems like there could be a lot of lessons learned for those trying to design interplanetary missions in trying to solve this problem here.
Right. So who did we give that today? This morning, we were talking to 100,000 high school kids.
Yeah.
We handed that to them, and they'll work on it. And in time, the world around, they were from all over the world, these students, and they will grasp these problems and they will solve them.
Well, I hope they will.
Oh, they will.
But robotic exploration, I mean, you know, having read quite a bit and about the heroic age of exploration here, Scott and Amundsen and Shackleton, and, you know, later into Byrd, all of those, you know, they're gripping tales of humans pushing the limits. When we take humans out, whether it's in Antarctica or, you know, in space, do we miss something?
I don't think so. The next exploration will be obviously the moon, maybe Mars after that. So people will go and live there anyway. But in terms of exploring here, why wouldn't you want to send a robot? Why do you want to send a person?
Well, you just got to talking about what a great experience it is to be here and to see it.
But it is also dangerous. And are we making great progress? No.
What will you miss about it?
I don't think I'll miss anything. I think I've grew up in Canada. I grew up always with ice, and I'll have lots of ice. I'll be back in a week playing ice hockey in Canada. So I'll miss nothing. It's just a beautiful part of the planet, and that's it.
Wherever you go, there's ice.
There is.
All right. David Holland, thank you very much. Appreciate your assessment of this epic voyage of the Aeron. And thank you all in the NOVA audience for your questions. We really enjoyed it. And we'll see you next time. For now, this is Miles O'Brien reporting live from the middle of the Southern Ocean. I just love saying that. Take care.